Now we shift from specific heat, which tells us how much energy is required to change temperature, to thermal conductivity, which tells us how easily heat can move through a material. Thermal conductivity is a measure of a material's ability to transmit heat by conduction. If a material has a high thermal conductivity, heat travels through it relatively easily. If it has a low thermal conductivity, heat has difficulty moving through it, and temperature differences persist longer. In steady-state conduction, the relationship we use is based on Fourier's law. Read aloud, it says, the rate of heat flow by conduction is proportional to three things: the thermal conductivity of the material, the area available for heat to flow through, and the temperature difference driving the heat flow. It is also inversely proportional to the thickness of the material, meaning that heat flow decreases when the distance heat must travel becomes larger. In the international system, thermal conductivity is typically reported in watts per meter per Kelvin. In the English system, it is often reported in British thermal units per hour, per foot, per degree Fahrenheit. Let's connect this to materials you already know. Liquid water has a thermal conductivity of about 0.6 watts per meter per Kelvin, while ice has a thermal conductivity of about 2.2 watts per meter per Kelvin. That means ice conducts heat much better than liquid water. This is one reason the thermal behavior of frozen foods can be quite different from the same food above freezing. The one-dimensional form of Fourier's law is the heat transfer rate by conduction equals thermal conductivity times area times temperature difference divided by thickness. Now let's use a simple numerical example to see what this means. Assume we have a flat slab of material. The area through which heat is flowing is 0.01 square meters. The thickness of the slab is 0.02 meters. The temperature difference across the slab is 20 degrees. First, let's calculate the conduction heat transfer rate when the thermal conductivity is like liquid water, about 0.6 watts per meter per Kelvin. Take 0.6 and multiply by the area. 0.01, that gives 0.006. Now multiply by the temperature difference, which is 20, that gives 0.12. Now divide by the thickness, which is 0.02. Dividing 0.12 by 0.02 gives 6. So for a water-like thermal conductivity, the conduction heat transfer rate is about 6 watts in this example. Now let's repeat the exact same scenario, but replace the material's thermal conductivity with a value like ice, about 2.2 watts per meter per Kelvin. Take 2.2 and multiply by the area, 0.01, that gives 0.022. Multiply by the temperature difference, 20, that gives 0.44. Divide by the thickness, 0.02. Dividing 0.44 by 0.02 gives 22. So in the same geometry and with the same temperature difference, an ice-like thermal conductivity produces about 22 watts of heat flow compared to about 6 watts for a water-like thermal conductivity. The takeaway is that heat transfer rate scales directly with thermal conductivity. If thermal conductivity increases, conduction becomes more effective and the rate of heat transfer increases, all else being equal. This also helps explain why freezing can change the thermal behavior of foods. Even though frozen foods can be harder to process in other ways, the ice phase can conduct heat more readily than liquid water in many cases. If we keep the area and the temperature difference the same and we double the thickness of the material, what happens to the conduction heat transfer rate? It drops by about half because thickness is in the denominator of the relationship. And if we keep everything else the same but increase thermal conductivity, the heat transfer rate increases proportionally.